Right then, let's get stuck into one of the absolute cornerstones of environmental science, dynamic equilibria. We're going to break down how our planet's natural systems perform this incredible balancing act, a concept that's not only vital for your A-levels, but for understanding the future of our world.
So, here's the plan. We'll kick things off with a big definition of dynamic equilibrium itself. Then we'll dive into the two key mechanisms that control it: negative feedback, which keeps things stable, and positive feedback, which can really ramp things up. After that, we'll look at the very real danger of tipping points, why having lots of diversity is so important for stability, and finally, we'll pull it all together to see what it means for us.
Okay, part one. What on earth is dynamic equilibrium? Honestly, get your head around this and everything else will click into place.
Have you ever stopped to think about it? For millions, even billions of years, our planet has been juggling all these massive interconnected cycles. The water cycle, the carbon cycle, you name it. And it's done it without completely running out of stuff or getting buried in its own waste. How? Well, the short answer is equilibrium.
And here is the official AQA definition you'll want to have in your back pocket. A dynamic equilibrium is all about balance, where different processes basically cancel each other out. A great way to think about it is like you're walking on a treadmill. You're always moving, that's the dynamic bit, but you're staying in the same spot. That's the equilibrium. In nature, this is what stops resources from getting used up and waste from piling up. That stable state, by the way, is also called homeostasis.
Section 2. Negative feedback. Now, this is the planet's go-to tool for keeping things steady and resisting change. It's the ultimate stabilizer.
Think of negative feedback like the thermostat in your house. If the room gets too warm, the heating clicks off to cool things down, bringing it back to where it should be. It counteracts the change. Positive feedback, on the other hand, is the total opposite. It's an accelerator. You know that horrible screech you get when a microphone is too close to a speaker? That's positive feedback. The sound gets amplified over and over again.
Let's look at some brilliant real-world examples. Say global temperatures start to creep up. That means more water evaporates, which forms more clouds. Those bright white clouds are great at reflecting sunlight back into space. We call that reflectivity albedo, which helps cool the Earth's surface, fighting that initial warming. Or if there's more CO2 in the air, plants can actually go into overdrive with photosynthesis, pulling that extra CO2 right back out of the atmosphere.
Let's just quickly walk through that hydrological cycle example step by step. So temperatures go up, which means more evaporation. That puts more water vapor up into the atmosphere. What happens next? Well, that vapor forms clouds and eventually comes back down as rain. This whole process helps to regulate temperature and keeps moisture levels balanced. It's a perfect little self-correcting loop.
All right, section 3, positive feedback. Now this is where things can get a bit scary. This is how small, tiny changes can spiral out of control into massive, system-changing events.
So the crucial thing to remember here is that while negative feedback calms things down, positive feedback amps them up. One change triggers another, which in turn makes the original change even bigger. It's like a runaway train, pushing a system further and further away from that stable balance point.
A classic and frankly quite worrying example of this is melting permafrost. As the planet warms up, this permanently frozen ground, mainly in the Arctic, starts to thaw. And when it does, it releases enormous amounts of methane gas that have been locked away for thousands of years. Now, methane is a super potent greenhouse gas, so that extra methane traps more heat, which, you guessed it, causes even more permafrost to melt, releasing even more methane. You can see how this cycle just dangerously fuels itself.
And it's not just the permafrost, Another huge one is the loss of albedo from melting sea ice. As the bright, reflective ice vanishes, it reveals the dark ocean underneath, which absorbs way more of the sun's heat, which in turn causes more ice to melt. You've also got similar accelerating loops with more forest fires and the release of methane from these ice-like crystals on the seabed called methane hydrates. All of these are pushing our climate further away from its happy place.
And that, unfortunately, leads us to a really serious consequence of all this unchecked positive feedback: the idea of an equilibrium tipping point. We're talking about the point of no return.
A tipping point is that moment when a positive feedback loop becomes so powerful that it just carries on by itself. The key phrase here, and you really need to remember this, is even with no further human action. It means we could, hypothetically, stop all our emissions tomorrow, but the process would have enough momentum to just keep going on its own, pushing the Earth towards a completely new and probably much less friendly equilibrium.
This quote really says it all, doesn't it? If we're going to get climate change under control, we absolutely have to do it before we hit these tipping points. It really is a race against time, and understanding these thresholds is one of the biggest challenges we face. So what are these big potential triggers? Well, your syllabus highlights a few key processes that could become unstoppable if we push them too far. Things like massive widespread forest fires, huge releases of those methane hydrates from the seabed, and of course, the complete melting of the Arctic permafrost.
Okay, let's switch gears for a moment. We've seen how these feedback loops work, but what makes a system strong and able to resist being pushed around in the first place? Well, in a word, diversity.
Just look at the difference here. On one side, you've got a complex, buzzing tropical rainforest full of living things, what we call biotic factors. It is incredibly resistant to change. On the other side, you've got a simple field of wheat, an agroecosystem. It's totally dominated by non-living or abiotic factors like the sun and rain, and it is so vulnerable.
So why is that? Well, it just makes sense, doesn't it? In a really complex ecosystem like a coral reef or rainforest, there are tons of different species, all connected in a massive web. If one type of plant struggles, the herbivores have other options to eat. If one prey animal has a tough year, the predators can just switch to eating something else. This whole web of interactions acts like a safety net, making the entire system much more stable and resilient.
Now compare that to a farm that's just growing one single crop, what we call a monoculture. There are no other food sources. There are hardly any natural predators to keep pests in check. It's an incredibly fragile setup. A single new disease or an outbreak of one type of pest can just rip through and destroy the entire crop. It's a catastrophic collapse waiting to happen. Low diversity means low resilience. Simple as that.
Right, let's bring this all home. Let's pull all these ideas together and see why they matter so much. Because this isn't just abstract theory for an exam paper, this is fundamental to our future on this planet.
At the end of the day, this is the whole point. The reason we study all of this, dynamic equilibria, feedback loops, biodiversity, is to learn from nature's rulebook. The ultimate goal is to use these principles to figure out how to build sustainable human societies that can actually live in balance with the planet instead of constantly shoving it towards these dangerous tipping points.
So, I'll leave you with this to think about. We've gone through the mechanisms that keep our planet stable and the triggers that could send it spiraling into a totally new state. Now that you understand how it all works, which of the potential tipping points that are on our horizon do you think we should be most concerned about, and why?